The law of mass action is a very important principle in physiology. The idea is that the rate of a chemical reaction is proportional to the product of the concentrations of the reactants. At chemical equilibrium, the rates of the forward and backward reactions must be equal. If the forward and backward reactions are equal, then there is no change in the concentrations of the reactants and products. Thus, for a chemical reaction mixture that's in equilibrium, the ratio of the concentration of the products to the concentration of the reactants is constant. So, for example, here we have an equation in which we have reactants A and B and products C and D. So, at equilibrium, the concentrations, which are shown here with the square brackets, of C multiplied by the concentration of D divided by the concentration of A multiplied by the concentration of B is equal to a constant at equilibrium. Okay, so again, we're talking about reversible reactions. We have reactants that can turn into products. Products can go backward towards the reactants, become reactants. Over time, this reaction eventually reaches an equilibrium. At equilibrium, the ratio, as I said earlier, of the product concentration to the reactant concentration is a constant value. This ratio is called the equilibrium constant, or KEQ. So that's shown here. You have as I said earlier, the concentration of the products divided by the concentration of the reactants. So here's a picture from your book. At equilibrium, we have two reactants, P and L, and the product in this case is just a bound form where P is bound to L. Okay, so again, so product over reactants means that the concentration of PL over concentration of P multiplied by the concentration of L equals a constant value, which is KEQ. So this example is from the textbook, and it's about protein binding. So the P stands for protein, and L stands for ligand. Okay, so the law of mass action says that when the protein binding is at equilibrium, the ratio of the bound and unbound components must remain constant. Now, what happens if you disrupt this equilibrium? Let's say we add either more P or L to the system. Then we have more reactants relative to the amount of products. What would you predict would happen to the forward reaction, which is R1? Right, so you probably guessed that R1 should increase. So what happens is if you increase either the amount of P or the concentration of P or the concentration of L, or say you increase the concentration of both of them, then they would have a higher probability of colliding and interacting. And so that would increase the forward reaction rate, and you would get more product, which is PL. So eventually, if we just add it and don't add any more, then you reach an equilibrium state. Now there's more P and there's more L, but there's also more of the product PL. And at equilibrium, KEQ would come back to being KEQ. In other words, this ratio would then equal KEQ again once more. Okay, so KEQ is a constant, so it doesn't actually change, but this temporarily would change. This ratio would change because you added more P or L or more P and L. So initially this ratio would change, but eventually, given that the temperature and other conditions like pressure and so forth are all constant, then eventually the system would come back to an equilibrium in which you'd have the same, in which this ratio here of PL over P multiplied by L would still equal the equilibrium constant. Okay, this thing brings us to the next idea, which is Le Chatelier's principle, or the equilibrium law. If there's disturbance in a system in equilibrium, the reaction will readjust to partially counteract the effect of the applied change, and a new equilibrium is established. So for example, here we have our reactants and products, a reversible interaction. We have some sort of disturbance, And the types of disturbance we typically talk about would be things like addition of chemicals, removal of chemicals, or a change in temperature. So let's look at the case of a buffer solution. A buffer solution makes use of Le Chatelier's principle to adjust its pH, and this prevents it from changing very much when an acid or base is added. A buffered solution is one that contains a relatively high concentration of both a weak acid and its conjugate base. Your blood contains the bicarbonate buffer system. So here's, for example, in your blood you have high carbon dioxide, water, carbonic acid, hydrogen ion, and bicarbonate. So in this particular instance, what's going on is you have a weak acid, which is the carbonic acid. A weak acid means that it has some propensity to give up a hydrogen ion or donate it to the solution, but it's not that strong. So at any given time, you wouldn't have all the hydrogen ion being donated to the solution. When carbonic acid gives up one hydrogen ion to the solution, it becomes bicarbonate, which is HCO3-. So bicarbonate is the conjugate base of the weak acid, which is carbonic acid. And it's a base because it can, of course, accept the hydrogen ion and then therefore become carbonic acid. In your body, this reaction is made much faster by the enzyme carbonic anhydrase. The reaction would go forward no matter what, but it would just take longer. Okay, let's look at this buffer system in a little bit of a detail. Imagine that there is an increase in hydrogen ion concentration in your blood. So we add a hydrogen ion. Will there be an increase in the forward or reverse reaction? Okay, go ahead and pause the video if you want to, and you can think about it. Okay, so if hydrogen ion is added, then we'd expect an increase in the backward reaction rate. And why would this occur? Well, the hydrogen ions collide more often with the bicarbonate ions, forming CO2 and water. So this, again, constitutes an increase in the rate of the reverse reaction. And the reaction equation is said to shift to the left. You're shifting to the left. What you expect to happen to the concentrations of the following: CO2, bicarbonate, and water. Okay, go ahead and pause again if you want to think about it and try and answer. Okay, so the answer is that if you're now favoring this backward reaction, or this reaction rate, the backward reaction rate is greater than the forward reaction rate, then the amount of CO2 should increase, the amount of water should increase, and actually the amount of bicarbonate would decrease. This would decrease because the hydrogen ion now has a higher chance of binding or colliding with the bicarbonate and therefore forming CO2 and water. To protect against added acid, the buffer solution must have a relatively high concentration of bicarbonate in the solution. Imagine that there's a decrease in hydrogen ion concentration in your blood. So hydrogen ion is removed. What will happen to forward and reverse reactions? Go ahead and pause it again if you want to think about this and answer. If H is removed, then we'd expect to have that the hydrogen ions will collide less often with the bicarbonate ions, forming less CO2 and water. And so you'd have a relative increase in the forward reaction rate compared to the backward reaction rate. So this reaction equation is said to shift to the right. What do you expect to happen to the concentration of the following: CO2, bicarbonate, and water? Go ahead and pause again if you want to try and answer on your own. Okay, if hydrogen ion is removed, then we'd expect, if you compare the backward and the forward reaction rates, and the forward reaction rate will be greater. So the idea is that CO2 and water would still collide and form carbonic acid, which would then give rise to hydrogen ion and bicarbonate. But since there's less hydrogen ion because you removed it, there'd be less chance of hydrogen ion colliding with the bicarbonate, and therefore you'd have a lower backward reaction rate compared to the forward reaction rate. So you'd expect there to be a decrease in CO2, a decrease in water, and an increase in bicarbonate. Let's look at the equation for a buffer system in general. So in this equation we have HA equals H plus plus A minus. A minus stands for anion, or a negative ion. When the acid is HA, the conjugate base is this anion, which has a negative charge now. So we can plug these numbers in. KEQ equals H plus concentration multiplied by the A minus concentration divided by the concentration of the acid, which is HA. If H plus is added to the solution, then the value on the right side of the equation becomes too high. And so to correct the value, then the A minus must decrease and HA must increase. The rate of the reverse reaction increases, and then the equilibrium shifts to the left. Okay, let's see if that makes sense. Yes, you've added, if a hydrogen ion is added, then it has a higher probability of colliding with A minus, the anion, and therefore you're going to have an increase in the backward reaction rate. So you'll have more of this HA being formed. So yes, that all makes sense. You basically can look at it both ways, and they both are consistent. Let's look at the equation for the bicarbonate buffer. So we have carbonic acid has a reversible reaction, in which it can donate hydrogen ion to the solution, and then you have bicarbonate, which is HCO3 minus. So if you plug these numbers in, KEQ equals H plus in brackets multiplied by bicarbonate acid in brackets, meaning their concentrations, divided by the carbonic acid concentration. So it's going to be the similar situation. If we add hydrogen ion to the solution, the value on the right side of the equation becomes too high. So to return to the correct value of KEQ, the bicarbonate concentration must decrease and the carbonic acid concentration must increase. And then again, and that also makes sense based on looking at the equation this way too. So summary of the law of mass action, Le Chatelier's principle. According to the law of mass action, at equilibrium, the ratio of the concentration of the products to the concentration of the reactants is constant. That's KEQ. According to Le Chatelier's principle, if the ratio is disturbed by adding or removing reactants or products, or changing the temperature, the reaction rates will change to restore equilibrium. Let's look at a couple more examples. If CO2 concentration in the body increases, what happens to the concentration of carbonic acid? What happens to pH? I'll let you answer that. Using this equation, predict what would happen if pH of the blood decreased. Okay, I think that's enough. We'll move on to the next topic.